Hi everyone. In this video, we're going to look at an integration technique called integration by parts. And because this technique is essentially just the reverse of the product rule for differentiation, we're going to start with a look at the product rule. So here is one way of expressing it. The derivative of u times v equals u times the derivative of v plus v times the derivative of u. So I'm going to rearrange this a little bit. So it becomes u dv equals the derivative of uv minus v du. And once I do that, I'm going to integrate because we're turning this into a rule for integration. So I integrate both sides of the equation, but the integral of a difference is the difference of the integrals, so I can just integrate each part of it. Once I do that, the integral of duv just is uv, so that part integrates. The other one's not so much, they're still integrals. So I have the integral of u times dv equals uv minus the integral of v du. This right here is the integration by parts formula for integration. So essentially what we do is we identify within our integral something that we will call u and something that we will call dv, and then we can swap it up. Now it seems not to have given me the answer to the integral, and it hasn't. It's just turned my integration into a different integration. So instead of integrating u, I'm having to integrate v, but in some cases that makes things a little easier. So the cases specifically, the sorts of situations where this is going to work very nicely, and we'll look at a bunch of examples, but it works really nicely if you have a function that is a product of something algebraic, so polynomials usually, and something transcendental, so trig or exponential or logarithmic. So any kind of function where we have some combination or some product of those two things, this ends up working beautifully. So let's look at some examples. Let's start out with we have the integral of x times the sine of x dx. Now we can see pretty quickly that a substitution isn't going to be helpful here because if I let u equal sine of x, the derivative is cosine of x. That x doesn't come from anywhere. However, if I consider that I can call this part, the x, I can call that u. So u equals x. And then everything else that's left, I can call dv. So dv equals the sine of x dx. Well, now what I need, so in my formula, I have u, I have v, I have du, and I have dv. So I need to figure out du, and I need to figure out v. So du is just dx. That's pretty straightforward because it is just a polynomial. And v, the antiderivative of sine, of x is negative cos of x. Now I don't worry about the plus c here because I'm actually not done. So when I'm finished with my whole integration, then I will have to remember the plus c. But for now, I don't really have to worry about that. So now that I have all four pieces that I need for the integration by parts formula, I'm going to plug it into that formula. So in other words, the integral of u times dv, so x times sine x dx, that's my original integral, equals u times v, so negative x cos x, minus the integral of v times du. Well, that's negative cos x dx. Well, this now gives me an integral I actually can figure out. So just to simplify it a little bit, I've got negative x cos x plus the integral of cos x dx. Now, essentially, I've gotten rid of that algebraic part of this. So this is equal to negative x cos x plus the sine of x. And here's where the plus c comes in. So this is the antiderivative that we were looking for right from the beginning. So these sorts of situations where we have an algebraic and some sort of transcendental, essentially I'm looking at, does this become simpler or more complicated when I integrate or derive? So when I have an algebraic polynomial type thing, it becomes simpler when I start deriving it. So I'm going to make that be u, because if x is u, then its derivative is going to be a constant. If, let's say, I had x cubed or x to the power 7, it's still going to become a simpler expression when I take its derivative. For the other function, sine of x, whether I derive it or integrate it, it doesn't become more or less complicated. So I'm going to make that the dv because it's easily anti-derived. All right, if that doesn't make fully sense just yet, that's okay. We'll do a bunch more examples and hopefully it starts to become a little clearer. So let's look at another situation where we have an algebraic function, so x squared in this case, multiplied by a transcendental exponential e to the power of x. So sticking with that same idea, I'm going to let u equal the algebraic part of it. So u is going to be x squared. Because I'm going to have to derive that to figure out du, and when I derive it, it becomes simpler. Du equals 2x dx. Everything else, so the x squared becomes u, everything else becomes dv. So dv equals e to the x dx, which doesn't get simpler or more complicated when I antiderive it. Its antiderivative is just e to the power of x. Now that I have all the pieces, I can put it into the formula. So I'm going to start with the integral of u dv, so x squared e to the x dx, that's just my original integral, equals u times v, so x squared e to the x, minus v times du, so 2x e to the x dx. That's all the parts from v and du. I've written them in a slightly different order just to kind of preserve the order that I was following before. But what I notice is that this new integral still has that same situation of a transcendental times a linear. So I don't panic, but I just do integration by parts again. So now I define a new u, in this case u equals 2x, so du equals 2dx, and v equals again e to the power of x dx, so same v as before, which means that dv equals e to the x. And I apply that formula one more time. So I still have x squared e to the x. I've got minus now sorry. So for this new integration by parts, I've got u defined as 2x, which means that du will be 2dx. And I've got dv still defined as e to the power of x dx, which means that v is still e to the power of x. So now I put these into that formula again. So I've still got my x squared e to the x. Now I've got minus u times v, which is 2x e to the x. And when I subtract now v du, I'm actually minus, so it's going to become plus the integral of 2e to the x dx, which I can finally integrate. So I've got x squared e to the power of x minus 2x e to the power of x plus 2e to the power of x plus c. So that's the antiderivative. So I can see the higher the power of that power of x, the more times I'm going to have to do integration by parts. If I had something to the power of 5, I would have to do it 5 times. That gets a little tedious, obviously, but once we've got the point across, we're not making you do it over and over and over again. So this is what we've got at this point. Let's look at an example where we've got cubed. This one we actually do something slightly different because I'm looking at this initially and I'm thinking, oh, well, if I'm following the same process, then I would have to actually do it 3 times because I'm going to make u equal x cubed and then it's going to be 3x squared dx and then I'm going to have to do it again. But actually, no, because if I set out to do that this first time, if I said, well, u equals x cubed and dv equals ln of x dx, I run into problems right away because I can't integrate ln of x. I don't know off the top of my head what its integral is. So I actually need something different. I can't do that. Remember what I said about things getting more or less complicated. The reason I made sine of x or e to the power of x be dv is because it was just as complicated when I integrated it as when I derived it. But that's not true for ln of x. ln of x actually gets simpler when I derive it. So if in this case I let u equal ln of x, when I derive it, I actually just get 1 over x dx. So in spite of the fact that when I make dv equal x cubed dx, it actually does increase in power when I integrate it. Because when I multiply it with the derivative of ln of x, it's just going to be a power, this becomes quite a bit simpler. So this is sort of the one exception. If you have an ln of x, you actually want that one to be u and not dv. So now when I put this into the integration by parts formula, I get that the integral of x cubed ln of x dx is equal to x to the power 4 over 4 times ln of x minus the integral of the product of v and du. So when I multiply 1 over x times x to the power 4 over 4, I get x to the power 3 over 4 dx, which is just a power that I can integrate. So I have x to the power 4 over 4 ln of x minus x to the power 4 over now 16 plus c. So when we have an ln of x, we usually want to make that u and not dv. All right, moving on to the next example. This one doesn't seem initially to fit the profile because it doesn't have a product. But again, I didn't know what the antiderivative of ln of x was off the top of my head. So I need a technique to find it. And what I just said, if you have ln of x, make that u. So u equals ln of x. That means that du equals 1 over x dx. And all that's left to be dv is dx, because I need every part of that original integral to be here. So that means v equals x. When I put this into the integration by parts formula, I've got the integral of u dv, so that's my original integral, equals u times v, so x ln of x, minus the integral of v times du. Well, when I multiply x times 1 over x, I just get x, or sorry, I just get 1. So I have a dx here. Well, that's the antiderivative of 1. So the antiderivative of 1 with respect to x is x. And then, of course, I have plus c. So that is how I antiderive the natural log of x. You could choose to memorize this one if you want. It's not one we would ask you again, but it's, not trivial. All right, there's one more situation that arises, and that is, what if I actually don't have a polynomial one? What if I have two different transcendentals? So what if I'm trying to antiderive cos x times e to the power of x? And this is a situation where the fact that cosine and sine keep flipping back and forth between each other when we derive or antiderive becomes useful, and e to the power of x just stays as it is. So it makes absolutely zero difference here whether you start by making u equal cos x or e to the power of x. Doesn't matter, because you can't ask yourself which one's more complicated if I derive it or antiderive it. They're equivalent. So just pick one. So I'm going to say here u equals cos of x, and dv therefore would have to equal e to the x dx. So du equals negative sine x dx, and v equals e to the power of x. All right, I'm going to stick these into the formula. So I've got the integral of cos x e to the x dx equals e to the x cos x. I don't know why I just switched orders there, but I did for some reason. Minus, which is actually going to become plus because I have a negative sine x. So plus the integral of sine x e to the x dx. All right, well, this hasn't really gotten me any closer. I'm still stuck with something I don't know how to integrate, so I'm going to do integration by parts again. Now, this is the important part. I could have chosen in the first case to make the trig u or to make it dv, and to make e to the power of x u or dv. But once I made that choice in the first use of the integration by parts formula, I have to do the same thing. So in other words, I can't suddenly decide to make u equal e to the x. That's going to not work. But because I used the trig function as u, I have to use the trig function as u again this time. So u equals sine x, and dv is still going to be e to the x dx. So du equals cos x dx and v equals e to the x dx. So this brings us full circle. I'm going to actually rewrite my original integral here. So the integral of cos x e to the x dx equals e to the x cos x plus e to the x sine x minus the integral of cos x e to the x dx. Well, I can see pretty quickly that this is just going to take me on a variety of loops, essentially, because I'm just going to alternate between sine and cos, while the e to the x always stays where it is. But what I now notice, I'm back to my original integral. So I can actually put them together. So I can write this as 2 times the integral of cos x e to the x dx equals e to the x cos x plus e to the x sine x, which means that the integral that I'm looking for, the integral of cos x e to the x dx, is just equal to 1/2 of that. So 1/2 of e to the x cos x plus 1/2 of e to the x sine x plus, of course, some constant. So in cases where you're just going to end up flipping back and forth between a sine and a cosine, then you can use this sort of iterative process. So for practice on these, in the Reed textbook, it's section 17.5, and in the Stewart textbook, it's section 11.4.